Okay, so we're back with example 2 where we're going to solve exponential equations that have a base of e. In example 1, we solved equations with a base of 10. When we solved in example 1, when there was a base of 10, we used a common log. This time, since the base is e, we're going to be taking the natural log of each side once we isolate that base of e raised to a variable exponent. So in example A, we're going to start by subtracting that constant to the other side, and we'll have e raised to the x minus 1 power equal to 15 minus 5, which is 10. And then step 2 is to take the natural log of both sides. So natural log of e to the x minus 1 is equal to the natural log of 10. And then we can use the inverse property. The natural log, remember, is a log base e. So log base e of e to the x minus 1 brings down that exponent of x minus 1, and that's equal to the natural log of 10. Then we can isolate the variable by adding 1 to both sides. And then we have x is equal to the natural log of 10 plus 1. And the natural log of 10 is a function on the 10. So remember, these are not like terms. You cannot combine the 10 and the 1. So we're going to put that in the calculator then to get a decimal approximation. Natural log of 10, close the parentheses, and then add 1. And we're going to round that to 4 decimal places to get x is approximately 3.3026. Because the fourth place value was a 5, the fifth place value is an 8, and so we round that 5 up to a 6. So to check that answer, we would substitute the rounded value back in for x, and we get 15.0001 on the left, which is very close to the 15 on the right. So using the rounded value, it's close enough to say that it checks. If you want to check with the equal sign, you need to use the exact value stored as your x. So 1 plus the common log of, or sorry, not common log, 1 plus the natural log of 10, and then store x, enter, and then we'll do e raised, oops, oh, lost it, let's try that again. So e raised to the x minus 1 power, and then the equal sign, oh, forgot the 5, plus 5, and then the equal sign, and a 15. So when we press enter, we get back a 1, which shows that that value checks. So then in example B, 7e to the 3x power equals 2, we first need to isolate the base of e to a variable exponent. So we'll divide both sides by 7. And now e to the 3x power is equal to 2/7. Okay, we're not going to use decimals because we lose accuracy if we have to round a decimal. So we're going to keep that 2/7 a fraction and move on to step 2, which is to take the natural log of both sides. So the natural log of e to the 3x power is equal to the natural log of 2/7. Okay, then our natural log and e, they cancel using the inverse property, and that brings down our exponent of 3x, which is equal to the natural log of the quantity 2/7. And then we can divide both sides by 3 or multiply by the reciprocal. That accomplishes the same thing. And x then is equal to 1/3 natural log of 2/7. So putting that in the calculator and rounding to 4 decimal places will be a negative 0.4176. And when we store that in the calculator in its rounded form, we get 1.999925, which is really close to the 2 that we started with originally. If you want to check it using the equal sign, you're going to store the original value here as the x. So the natural log of 2/7 divided by 3, store x. And then we'll type in the original 7e raised to the 3x power equals 2 and press enter, and we get a 1, which tells us that that answer checks. So go ahead and pause the video to try this problem on your own on scratch paper or dry erase board. 2e to the 2x power equals 10e to the -5. There's a hint up in the side here with the properties of exponents, if that helps you if you get stuck. And then when you're ready to go over the answer, you can resume the video. Okay, so I started by dividing both sides by e to the -5 so I could get my base of e together on one side. And that gives me 2e to the 2x over e to the -5 equals 10. And then our properties of exponents say that when you divide the same base, you subtract the exponents. 2x minus a -5 gives us 2x plus 5. So we have 2e to the 2x plus 5 power equals 10. Then we're wanting to get the base of e by itself, so we divide both sides by that coefficient of 2. And now e to the 2x plus 5 is isolated on one side of the equal sign, and it's equal to 5. Then we're ready for step 2, which is to take the natural log of both sides and use the inverse property to bring down that exponent of 2x plus 5, and that's equal to the natural log of 5. Then we're going to subtract the constant from both sides and divide by 2 to get -5 plus the natural log of 5 all over 2. And that rounds to approximately -1.6953. When we check that, it shows that it works.